We're now going to start talking about the differences between concurrent and non-concurrent collectors in more detail than we've talked about before. I've obliquely and briefly mentioned the differences between these different types of collectors a number of times in the past, but now we're really going to start delving into this. So first, let's just do a quick recap of what a collector is. Collector defines an interface whose implementations can accumulate input elements into this so-called mutable result container. We talked about that. You've seen a bunch of examples of predefined non-concurrent collectors, like the collectors returned from toList and toSet and toMap. You've also seen examples of user-defined or application programmer-defined collectors, such as some of the ones we looked at for the simple search stream gang program case study. And you've also implemented a user-defined collector, array collector for your programming assignments. What we're now going to do is talk about some of the characteristics of collectors. So collectors can have a number of different characteristics, and one of the key characteristics here is whether they're concurrent or non-concurrent. And these are actually set by a set of flags that you get with the characteristics type. It's an enum. The distinction between concurrent and non-concurrent really only matters for parallel streams. For sequential streams, it doesn't matter if your collector is concurrent or non-concurrent because it's only going to be called in one thread. You can use a concurrent collector for a sequential stream. It's probably overkill, but it's certainly possible. Where this really matters, though, is when you have parallel streams, and then it makes a big difference, and you've got to get it right, otherwise you'll get erroneous results. Interestingly enough, and this is sometimes a bit non-intuitive at first glance, a non-concurrent collector can be used for either a sequential or a parallel stream, and the Java Streams framework makes sure that the semantics are preserved correctly, irrespective of what type of stream is used. Right now, we're just going to focus on parallel streams, but be aware that you could also do what we're about to talk about for sequential streams as well. So let's talk about the structure and functionality of the so-called non-concurrent collectors. So remember, a non-concurrent collector operates by merging subresults. We took a look at some examples of that just a little while ago when we were talking about things like the Shakespeare word system that was using tree sets in order to come up with a list of all the unique words in Shakespeare. Just another quick recap. I think you probably know this by now. The splitterators partition the input up into chunks. Those chunks are then run in parallel in the common fork join pool. That's the apply phase. And then finally, the subresults of each chunks are collected into an intermediate mutable result container, which would be a list or a set or a map or whatever you want to define, an unsynchronized array, as we've done, and so on. Different threads operate on different instances of these intermediate result containers. And that's all managed internally by the Java Streams framework. You don't have to worry about creating those intermediate result containers. It's done for you. You just have to provide the appropriate factory methods, like the supplier that makes the appropriate intermediate mutable result container. And then again, the framework makes sure that the subresults are all merged together into a single mutable result container when all is said and done at the end of the processing to get the final reduced result. As we talked about before, only one thread in the fork join pool is ever used to merge any given pair of intermediate subresults. So as a result, there's no need for you to put locks in your code when you're doing non-concurrent collectors. So that makes life a lot easier. This process is safe in the sense it's thread safe. It's order preserving in the sense that if you have things like in counter order, that's easy to preserve. But it can be costly for complex collections like maps and sets, because in that particular case, you've got to be able to merge things into maps and sets, and that takes a while because the merging process doesn't come for free, whereas it's very simple to do it with lists because you just tack one list at the end of another list. So let's now talk about the structure and functionality of so-called concurrent collectors. So a concurrent collector creates a single concurrent mutable result container. Concurrent here means that it's thread safe. It's got synchronizers to protect its internal state from corruption and race conditions. And that then will accumulate elements from multiple threads that are running in the parallel stream, actually more specifically running in the common fork join pool for the parallel stream. As usual, the input's partitioned into chunks by the splitterators, no change there. Each chunk runs in parallel on the common fork join pool, no change there. Where things do change is that the subresults are collected into a single mutable result container. And this has to be some kind of concurrent collection or a synchronized collection or a collection that's been explicitly synchronized by things like synchronized blocks or reentrant locks or stamp locks or whatever kind of locks you need to use to make things synchronized. Most commonly, you would probably just use a concurrent collection that comes out of the box with Java and the Java class library. So as a consequence, in this case, different threads in the parallel stream share one concurrent result container. So there's one container, it's shared by all the threads. There's not intermediate containers that are used and then merged together and so on and so forth. So as a consequence, there's no need to do any merging, which is often faster, especially for complicated data types like sets or maps. However, encounter order is not preserved, and some kind of synchronization is required on the concurrent collection. Otherwise, you'll get race conditions. And I should hasten to note that you're responsible for getting that right. The framework won't save you if you mark a collector as being a concurrent collector and then just use an array list or something that doesn't have any synchronization built into it. Now, which approach should you use? Well, a concurrent collector may outperform a non-concurrent collector under certain circumstances. And one of the key circumstances is if the merging costs are higher than the synchronization costs. So you'll have synchronization, but synchronization can be pretty darn fast. But merging, especially for complex data types like sets and maps, that may actually be more expensive than the synchronization. So to get a feeling for the trade-offs, there's an example here that's the EX14 example that demonstrates these trade-offs. Now, one of the things that's worth considering here is that there are some really highly optimized concurrent containers that come out of the box with the Java class library and the Java collections framework. So for instance, the concurrent hash map, which is a very, very super duper optimized concurrent collection that comes out of the box with Java, that actually may be faster to use from multiple threads to add elements than merging multiple hash maps with non-concurrent collectors. And you can take a look, there's some good examples here that compare and contrast the overheads of these different approaches in this article at the bottom of the page. Concurrent hash map is also typically more efficient than something called a synchronized map. And the main reason for that is that concurrent hash map has lots of separate synchronizers so that you don't end up having to pay the cost and the contention of a single lock for the entire collection. In contrast, a synchronized lock has a single lock. And so as a result, when lots of threads are pounding away, either adding to it or reading from it, you'll end up with a bottleneck there and more contention. So learning to use the right collections is very important if you're using some kind of concurrent collector. So that's a quick overview of the non-concurrent and concurrent collectors. And then what we're going to do next is we're going to look into more detail about how to implement them and how they work under the hood and what the methods are and the API calls that you need to be aware of and how you need to make sure you provide the right kind of accumulator method to add elements into the mutable result container, which also needs to be synchronized or concurrent if you're doing a concurrent collector.